Related rates. It's going to be an equation involving two or more variables. That's fine. Differentiable functions of time. Now this is totally new. We're going to do the derivative d dt. We're going to do the derivative with respect to time. Up till now, it's been, let's write down something like this. Might have x's and y's in them. We've been doing d dx to every term, the derivative with respect to the variable x. So when we got to x's, there was no need, the 6x squared, there's no need for dy dx kind of thing. We're going to do these with respect to time. None of them will have t in them. So then what we're going to have is multiple d something dt's. There'll be multiple of, like, when we do this one, 2y dy dx. Multiple of those, which are rates of change. Then what we'll do is implicit differentiation. So here's a general strategy. So you are going to draw a picture. Oh, that's right, I just separated. It's not essential, but it really helps outline what we're going to do. So you draw a picture, write an equation. This might be the most important part. What equation represents the picture? It'll be like our formula or an equation that we know. Differentiate in respect to time. I put d dt. Differentiate implicitly. So we're going to do d dt to every term. And finally, we will then substitute in values and solve. I'll show you in this first one how substituting, you can sometimes substitute to start, but I'm going to frown upon that because what can happen is you could take the picture at one moment in time. It's easier to explain once we do this one. One moment in time, freezing the picture, and it just causes the problem to be thrown off. So I encourage you to substitute at the end. Okay, so here we go. Let's try one. So now you're like, okay, once we see an example, it's better to see what's going on. All right, we got a ladder. It is 20 feet and is leaning against a building. So here's my building. This is my ladder. We can assume the building, doesn't say, but the building is not crooked. So I could put a right angle in there. I'm not going to put 20 in. So you might want to label it, like, don't label 20 yet. It will be. It's not there yet. Here's what's happening. If the bottom of the ladder, so here's the bottom of the ladder, is sliding along the pavement away from the building. Right, so that the bottom there is sliding away. It's going at 1 foot per second. I'm just going to write here 1 foot per second. At one moment in time, it's at 1 foot per second. It'll change. It's a rate of change. How fast is the top of the ladder, here's the top of the ladder, moving down the wall? That's the question right there. Let's put a question. How fast is the top of the ladder moving down when the foot, in other words, the foot is the base of the ladder, the bottom. When the base of the ladder is 5 feet from the wall. Okay, so a lot going on there. You've got a couple lengths, 5 feet, the ladder's 20. This is sliding away 1 foot per second. What's the rate of change that it's going down? Let's take it back to the steps above. Draw a picture. We did. I'll label things in a second. Next step, write an equation. So guys, we're going to have this length, the ladder length. We can get that length, and we have this length, and it's a right triangle. Do you know an equation that relates the three sides? Pythagorean theorem. So that's our equation. There are many that are Pythagorean theorem. Sometimes it's just a formula. It might be like a shape formula or something. They might give it to you. Just one way to think of Pythagorean theorem. Okay, that's our equation. Next step, I believe, is just differentiate, right? Differentiate implicitly. So notice, I'll show you later how we could have substituted now, but let's go ahead and differentiate first. So I'm usually doing d dx. Here I'm going to do d dt, which means the derivative with respect to the variable time. The variable t, which is time. And you might say none of those have t in them. That's correct. So every single one will have like usually dy dx. Everyone will have dt d something. So let's do each of these. The derivative of a squared is 2a. It's like x squared would be 2x. What I'm really doing though is chain rule. We write it over here. 2, subtract 1, bring down the a, then the derivative of a with respect to time is dA dt. dA dt. That is the derivative of a. Oh, by the way, I'm going to. A is going to be bottom. I can make A or B the bottom or side one. The rate of change of this length with respect to time. That's what each of these, when you see that, is a rate of change. The next two are the same thing but with B in them. And C. So the next one is 2B times the derivative of B, which is dB dt, equals, and then 2C dC dt. So even though there was no t to start with, we can still do this because we will actually know certain rates of change in respect to time. So once we get, guys, once you know the formula, you do this, it's mostly plugging things in now. So how about any questions up to now? Did okay? All right, well, I am going to do one thing to simplify. Sorry with you if I cancel out the 2's. I'm dividing, I'm not going to write it, but I'm dividing every single term by 2. You don't have to, it just makes it easier though. And now I'm going to plug things in. Okay. So let's go back. I labeled it A, B, and C. Let me draw on the actual numbers I know. C, the ladder, was 20. They're asking when the base or the foot of the ladder is 5 feet from the wall. That's when A is 5. So over here, I'm going to put in 5 for A. Just draw each of these directly below. I don't have B yet. Over here, I have C, though. It's 20. So then, to get B, we'll actually need that. I just fill in B there, and I can do the Pythagorean theorem. So I have the ladder's 20, A is 5. I can do the Pythagorean theorem. So this one we'll need a little extra work just to find it. B squared plus 5 squared equals 20 squared. So this will be 25. 20 squared is 400. Subtract 25. So I got B squared equals 375. And do a square root. So B will be, we'll just leave it like that, square root of 375. Cool. So I'm plugging that in for B. This is A. Let's see. So we go with the A, B, and C ones. C the ladder, A the bottom, and I had to solve for B. Some of these might do a little extra work to solve for one thing. Okay, what?
So like, what's the point of doing the dA dt?
Those are rates of change. I'm going to fill those in now.
Okay.
Yeah, I know 2 of them, and one of them is what they're asking for. So let's go up. The question is, how fast is the top of the ladder moving down? That was this one. That's the rate of change of what I call B. So is how fast B was changing? So they're asking me to solve for this one. So I'm just going to bring this one down. Or sometimes students want to call this x, so it doesn't look as crazy here, dB dt. So you can call it x. That's the one we're finding, though. The other two I know. The 1 foot per second, that was this one. I already labeled it here. How fast my A is changing. Set up here. The bottom of the ladder, is sliding along the pavement away from the building here at 1 foot per second. So that's 1, dA dt. dA dt is 1. And the other one I need right here is dC dt. I want to see if you guys know this one. C is the ladder. What's the rate of change of the length of C, the ladder? 0. It's not changing. Okay. And so that's it. Substitute in, knowing where to plug things, and then it's an easy solve for dBdt. Before we do that, I wanted to tell you this. So if something is not changing, you would be allowed to plug it in. So my actual equation, another way to do it, I could have done a squared plus b squared equals 20 squared, since the length of the ladder was not changing. Don't have to. I like doing it this way, just writing the formula, doing it all first, and then plugging things in. But if and only if something is not changing, you could plug it in. And you can see if we did the derivative of this, it would still be 0. So you get the same thing. Okay, let's work it out. This is 5. This is radical 375 dBdt. And that was 0. I'm solving for this one, so I subtract 5. So the radical 375 dBdt equals negative 5. And then I divide by radical 375. Okay, and then calculator. Oh, here. I'm not going to take a lot of time for this, just super short on time today. It would be about, rounding, about negative 0.258 feet per second. The negative is okay, because that represents it's going down. Yes. So that's why negative. Okay. We should have time to do one more today to finish up. Yeah, might be a little rushed, but I think I can do it. Any thoughts? Anything I can clarify on that one?
It's just fixed, no point.
It is. It's a quick thing. It doesn't look like it's sticking though. I can see it on the ground though.
It's not cold enough to stick.
Yeah. So let's turn it over to the top one on the next page to finish up. A hot air balloon rising straight up. So a hot air balloon off the ground. That is a good hot air balloon. It's a hot air balloon, clearly. Okay, let me draw the little wicker basket thing.
Oh, that.
Oh, well, that didn't.
That did not.
Right, it's like a basket thing.
We gotta have like the fire and the strings.
Oh, I didn't need a little gap in between
Yeah.
there. Yeah.
Come on.
My bad.
I'm upset.
This is why I'm not an artist.
Anybody can be an artist, mister.
Really?
Yeah, anybody.
I do not have skill in art. You're right. I haven't practiced since about 4th grade.
Mr. Bibler told me that. He said anybody can be an artist.
That's how I feel sometimes about music. Somebody's like, "Well, I can't learn the guitar." I'm like, "Well, you just need to practice. You really." You're right. I think at some point to be really good at it, you probably
yeah, but
need a little.
I think anybody can
practice.
be decent.
We're getting off track now. The hot air balloon rises straight up. That means I know that this is not changing. Right? It's straight up. I'm gonna call this RF. It's tracked by a rangefinder 500 feet from the liftoff
Did
point.
you see my board?
Here was I'll just write liftoff. It was right there. A rangefinder, it's just a device to get an angle measure. No, it's a device to get distance. Measure distance. At the moment that this device, the rangefinder, finds angle of elevation. So if your angle of elevation is here, angle up. It is a triangle. It will not be Pythagorean theorem this time. At the moment the angle is pi over 4. Now this angle, I'm going to call it theta. Yes, it will be pi over 4. Here's where you don't substitute pi over 4 yet. Okay, it should all be variables at first. The angle will be increasing at the rate of 0.14 radians per minute. That rate of change of this angle. In other words, d theta dt. How fast is the balloon rising? We're going to call this h. How fast is the balloon rising? The question is asking for dh dt, the rate of change of the height. Okay, and we can assume it's a right angle here. Now, the other part I know is the 500, that's the base. We for now call it x, this base here. I do not have the hypotenuse, so I'm not going to be able to do Pythagorean theorem. Can you guys think of something that relates an angle with these two sides?
Sine plus 13.
Correct, Trig. Which one?
So it's adjacent and opposite.
This is adjacent, this is opposite. So it's
So,
which one? Tangent. It's tangent, very nice. Tangent of our angle, which is theta, is opposite over adjacent, h over x. So again, step 1 was draw a picture. Step 2 was write an equation. That's the equation. Step 3 is differentiate implicitly, and then plug in values. Okay, let's make this one easier for ourselves. We could just differentiate and then plug things in. The 500 is not changing, right? The balloon's going straight up.
Yeah.
They gave us up there. It's the range right at 500 feet along there. That is not changing. I am allowed to plug in. I shy away from this, but I'm a little short on time, and so I'd rather just let's plug it in. I can show you both ways, but that's what I'd be at. Let me write this an easier way. Isn't that really like h over, if it was h over 2, can I write it like 1/2 h? Is this really 1 over 2?
Sure.
So this, can't I write as really 1/500 h? Okay. Now I will do, I just made it a little simpler for us. Now I will do, this is like step 3, d dt to both sides, both terms. This is one term, like 1/2 h, 1/500 h. When I do the derivative of the left side, tangent, it is secant squared of theta, yeah, I bring the theta down of the inside, times the derivative of this chain rule, derivative of theta, which is d theta dt. It's a little tight there. Secant squared theta, well, that's not working. Secant squared theta times derivative of theta, which is d theta dt. Over here, I mean, if it was like 2h, the derivative would be 2, right? So 1/500th h, the derivative is 1/500. But it's a chain rule. I need the derivative of h, which is dh dt. In every single one of these that you do, when you do a variable, it should have d whatever dt. Okay, that's it. We substitute values in. Let's see what we have. They're asking for how, oh, they're asking for this. So they're asking for dh dt right here.
So you just times.
Yeah, we could already do that and then plug things in. Times both sides by 500. So that's what we're going to do. Is 500 secant squared, we'll plug in an angle, and then d theta dt. Something right here. 500 secant squared of, they gave us the angle, pi over 4. The angle of elevation, yep, pi over 4. And then d theta dt, that's the rate of change of the angle. When it is increasing at the rate of 0.14 radians per minute. So d theta dt, I'm putting right here, times 0.14. You can evaluate cosine of pi over 4 and flip it if you'd like, and then square it. Or if you know secant of pi over 4, and then square it. But just for time's sake, you put this in, and you get 140 feet per minute. One quick thing to finish up, I do have a minute or two left. If you had not plugged in 500, let's say you had not plugged in 500, on the right side, you would have had h over x. You would have just then had to do quotient rule. Low d high minus high d low over low squared. The rate of change of the x was not changing, it was 0. Then you cancel this out, and it would have been the same as what we had before. 1 over x is 500 dh dt. It ends up being the same. Okay, we'll finish the third one tomorrow.